Hi lovers of numbers and music. In this second video on partitions, we're going to look at how permutations of partitions are made. Again, we're in the programming language Max that's used for music, sound and video. We'll start from where we left off. In the first episode, we created partitions of a certain integer number by sending the integer number to the bark.partition object. This is a better alternative than using JavaScript, which we also showed last time. So we can take the partitions of, say, the number 4, and it tells us that there are 5 partitions, or the number 7, it tells us there are 15 different partitions, or the number 12, for example, it tells us that there are 77 different ways of partitioning the number 12. We can access these different partitions of the number using an index, which is this is the index according to the descending rule. This is the index according to the ascending rule. They are easy to convert from one to the other by doing a little bit of arithmetic, and we can convert from the descending rule to the ascending rule by doing this arithmetic and then reversing the string that results from the descending rule to get the string for the ascending rule. So if we look at the number 7, for example, we can go through the different partitions starting from 1 according to the descending rule, 7, a 4 and a 3, 5 and a 2, 3 and 2 2s, etc., going through until eventually we'll have nothing but 7 1s. The same is true for the 15 partitions that are generated according to the ascending rule, except here we start from the first index, then that's the 4 1s, and then as we go up the indices we're getting fewer numbers, and eventually we'll get to just the number 7 as it's unpartitioned, the whole number itself. Now let's see what happens if we take permutations of these partitions. It's easy to do because we have a useful object, bark.perm, that does permutations, and this produces only the unique permutations so it eliminates all duplicates, which is very useful for our purpose because that's usually what we want to get, is only the unique permutations. So let's see what happens if we find an interesting partition that has different numbers. For example, if we go through number 7 and we get to the 7th index, or index 7 of the partition of the number 7, we get something which has 3 different numbers in it. And let's see, when we take that and we see what it gives us for the permutations, it gives us 6 different permutations. This is kind of what we expect, because if we look at permutations of different numbers, we expect to get factorial 3 out of 3 numbers, and it gives us 6 permutations, and that's what we get, 6 permutations. Now if we had an example where there were duplicate numbers, so let's look for one with duplicate numbers, say this one, the next one, the 8th partition, we would expect in all to get 24 different permutations of this, but we find that most of them are duplicates, and it only gives us 4 unique permutations, because here the 1 is kind of rotated through the number 2, so that there are only 4 different variations. So the number of permutations you actually get will depend on, amongst other things, the number of unique items that are in this string. Let's see what we can do. Once we've got here a certain number of permutations, we can display them, for example, in different ways. I've got a little box here that will display them as a musical scale. So let's take, for a musical scale it kind of makes sense to partition the number 12, because that's the number of semitones in an octave. So it tells us that there are 77 different permutations of the number 12. Let's scroll through them for a moment to find something that has quite a lot of different, or quite a few numbers in it. For example, this might be a good one. 3, 2, 2, 2, 2, 1. When converted to a scale, we'd expect that to comprise a minor third and 4 consecutive whole tones, and then a semitone. And so if we choose the first permutation of that, first unique permutation of that, that's exactly what we get. We get a minor third, then 1, 2, 3, 4 whole tones and a semitone. But of course, as we go through the unique permutations and display them as a scale, we'll get these 6-note scales, or a 6-note scale before it repeats at the octave. But the minor third will be in different places, and the whole tones will be in different places, and the semitone step will be in different places. So let's go through. There are 30 different variations on this 6-note scale, comprising these particular intervals. That's the inverse of the first version, and then the minor third moves to a different place, and so on. Let's hear what this sounds like, this particular scale. And of course there are 30 different versions of this scale. So we've now worked out a way of, as it were, surveying all the different ways of dividing up the octave using these particular intervals. So it may be an idea to look at what kind of properties the partition that we are generating has, what kind of intervals it contains, and how many items it contains, and so on. And this would enable us to do a search and find partitions with particular properties. So that's what we'll do in the next video. Bye for now.